This video is going to discuss how when we modify an equation, it makes a change to the graph of the function. Before we get started though, I'd like to do a quick review of those toolkit functions that we talked about earlier. So earlier in this course, we learned about the shapes of some basic functions. Y equals x squared is our basic parabola. It has this kind of U shape. The vertex or the bending point is at the origin, goes through the point 1, 1, negative 1, 1 as well. Y equals x cubed also goes through the origin, but the difference is the right side goes up and the left side goes down. That's because when you cube a negative number, you end up getting a negative. Y equals the absolute value of x. This function looks like a V. It also goes through the origin. And the right side of the graph actually looks like the line y equals x. The left side of the graph looks like the line y equals negative x. Here's our square root function. Looks like half of a sideways parabola goes through the origin. 1, 1. Square root of 4 is 2, so 4, 2. The cube root function looks similar to our square root function, except there is a left side of the graph. That's because you can take the cube root of a negative number and you'll get a negative number. So it goes through the origin, goes through the point 1, 1, also goes through the point negative 1, negative 1. It does kind of look like a reflected version of that y equals x cubed as well. And then finally, here's the graph of our reciprocal function. Our reciprocal function goes through the point 1, 1. And as you approach x equals 0 on the right, the graph goes up very steeply. And on the left, the graph is actually approaching y equals 0. As you plug in numbers that are bigger and bigger for x, the y values are getting smaller and smaller. The graph has a similar shape on the left side. It goes through the point negative 1, 1. As you plug in values with larger and larger magnitudes that are negative, it approaches the x-axis or y equals 0. And then as your x values are approaching 0, the graph is actually going down towards that y-axis. So in this section, what we're going to be doing is talking about how when we modify equations, it modifies the shape of those basic toolkit functions. So we're going to start by looking at vertical shifts. If you add or subtract a constant to a function, this is considered an output transformation. It's happening outside of the function. It's going to impact the y values, and we're going to do exactly what it says. If c is positive, we're going to move the graph up c units. If c is negative, if we're subtracting our constant, we're actually going to move our graph down c units. Let's see how this works with some examples. Sketch the graph of f of x equals absolute value of x plus 2. So notice that plus 2 is outside of the absolute value. That's what makes this an output transformation that impacts our y values. So I'm going to start by just drawing my toolkit function. This is a graph of absolute value of x. Our V-shaped graph goes through the origin 1, 1, negative 1, 1. This plus 2, again, output transformation impacts y values. So we're just going to add 2 to all of the y values. This is going to take the graph and actually move it up 2 units. So I picked 3 points on the graph of my absolute value function, and I just moved them up 2 units, adding 2 to those y values. And there is the graph of f of x equals absolute value of x plus 2. Here's a second example. Sketch the graph of f of x equals square root of x minus 3. I'll draw my parent function. There's my square root function. Goes through the origin. 1, 1, 4, 2. Again, notice the minus 3 is outside of the square root. This is an output transformation. It's going to impact our y values. It says minus 3, so we're going to minus 3 from all of our y values. This is going to take that graph and shift it down 3 units. So I took a couple points on the graph, like the point at the origin, and I moved it down 3 units. Did the same for all of the points. Connect the dots, and there's my graph. Same shape, but shifted down 3 units. All right, what happens if we put our constant inside the parentheses or inside the function? This is now considered an input transformation. It's going to impact our x values. And it turns out with input transformations, we're always going to do the opposite of what it says. So if that c is a positive number, if we have a plus a number, we're actually going to be moving the graph left c units, or subtracting that value from our x's. If the c is a negative number, if it's minus a number, that's actually going to shift our graph to the right c units. And again, let's just take a look at some examples to see how this works. So if I want to graph f of x equals quantity x minus 3 squared, I'll draw my parent function, which is y equals x squared, or my basic parabola. Goes through the origin, 1, 1, negative 1, 1. Now, notice that the minus 3 is inside the parentheses. That's how I know this is an input transformation, and it's going to impact my x values. We're going to be doing the opposite of what it says. It says minus 3, so I'm actually going to add 3 to all of my x values. And what this is actually going to do is take the graph and shift it to the right 3 units. So that point that was at the origin, if I add 3 to the x value, that moves that to the point 3, 0. And the entire graph, entire shape, gets shifted to the right 3 units. All right, one more example. F of x equals the square root of x plus 2. There's my parent function, my square root function. Goes through the origin, 1, 1, and 4, 2. The plus 2 is inside the square root. That means it's an input transformation. It says plus 2. I'm going to do the opposite. I'm actually going to subtract 2 from all of my x values. And that's going to take this graph and shift it to the left 2 units. So I take each of the points I found, minus 2 from the x values. That just moves them to the left 2 units. And in purple is the graph of f of x equal the square root of x plus 2. Now we can combine these transformations together. I can graph f of x equals absolute value of x plus 1 minus 2. There are 2 different transformations happening here, an input transformation and an output transformation. Once again, I'll start by drawing my parent function. This time it's an absolute value. Looks like that v goes through the origin, 1, 1, negative 1, 1. The plus 1 that is inside the absolute value is my input transformation. It's going to impact my x values, and I'll be subtracting 1 from all of the x values. That's going to take this graph and shift it to the left 1. The minus 2 occurs outside of the absolute value. That's my output transformation. That's going to impact my y values. I'm going to do exactly what it says. It says minus 2, so I'm going to subtract 2 from the y values, and that's going to take this graph and shift it down 2 units. I can do these transformations in either order. It doesn't matter which one I do first. I'll do the shift left one first. So I took my absolute value v, and I shifted it to the left 1 unit. And then to finish, I'm going to take that result and shift it down 2 units. And in purple is my final answer. That's what the graph of f of x equals absolute value of x plus 1 minus 2 looks like. So adding or subtracting numbers gives us shifts. If the number is outside of the function, it's a vertical shift. If it's inside of that function, it's going to be a horizontal shift. All right, what if we multiply a function by a number? So if we multiply a function by a number, again, the pattern is if the multiplication is outside of the function, it's an output transformation. It's going to impact our y values, and we're going to do exactly what it says. If that number happens to be bigger than 1, we're going to be multiplying all of our y values by a number that's bigger than 1. And what that's going to do is it's going to take the graph and stretch it vertically. If that number happens to be smaller than 1, and for now let's just consider positive multipliers. So if that number is smaller than 1, we're going to multiply our y values by the number, but that's actually going to shrink it or compress it vertically. So again, we'll take a look at a couple examples. If I want to graph 3x squared, I start by graphing my parent function. That's my basic parabola, goes through the origin. The 3 is happening outside of the parentheses or outside of the function, so it's going to impact my y values. We are multiplying by 3, so I'm going to take all of my y values and multiply them by 3. So that means the point that is at the origin actually stays there because 0 times 3 is 0. But the point that was at 1, 1, if I take that y value and I triple it, I multiply it by 3, it's going to move to the point 1, 3. The same thing happens on the left. The point that was at negative 1, 1, I take the y value, I triple it, and it moves to negative 1, 3. And there's my result. I get the same shape. It's a parabola. It looks a little bit skinnier because it's actually been stretched vertically. Now, if I put a constant multiplier that is smaller than 1, like a half, let's graph f of x equals 1/2 times x cubed. I start by graphing my parent function. So it goes to the origin, 1, 1, negative 1, negative 1. So the 1/2 is our multiplier. We are going to multiply all of our y values by 1/2. We're going to cut our y values in half, and this is going to be a vertical compression. This is going to squash the graph. So the point that was at the origin is still going to stay there because 0 times a half is still 0. But the point that was at 1, 1, we take the y value and we cut it in half, and it moves to 1/2. Same idea with the point that was at negative 1, negative 1. I cut the y value in half, and it's at negative 1/2. And there's my result. My graph has been squashed or vertically compressed. All right, what if that multiplier is inside the function or inside the parentheses? This is an input transformation. It's going to impact our x values, and we are going to do the opposite of what it says. So that means whatever number is being multiplied by our x, opposite would be dividing by that value. So if that number is bigger than 1, and we divide by that value, it's going to compress our graph horizontally. If that value is smaller than 1, and again, for now, we're just considering positives, that is actually going to stretch our graph horizontally. Let's see what this looks like by solving a couple problems. Let's sketch the graph of the quantity 2x squared. So I draw my parent function, which is my basic parabola. And this time, I notice that the 2 is inside the parentheses. That tells me that this is an input transformation. It's going to impact my x values. And I'm going to do the opposite of what it says. It says 2 times x. So I'm going to take all of my x values and divide them by 2. This is going to give me a horizontal compression. So the point that was at the origin stays there. 0 divided by 2 is still 0. But the point that was at 1, 1, I take the x value, I cut it in half, and it moves to 1/2, 1. My parent function should contain the point 2, 4. Same idea. I cut that x value in half, and it should be at the point 1, 4. And there is my graph in purple. It has the same shape, but it's been horizontally compressed. All right, let's graph f of x equals the square root of 1/3 times x. I'm going to draw my parent function, which is my square root function. Notice the 1/3 is inside the parentheses, so this is an input transformation. And we are going to do the opposite of what it says. It says times 1/3. The opposite of times 1/3 would be divide by 1/3 or multiply by 3. So I'm going to take all of my x values and multiply them by 3. This is going to give me a horizontal stretch. So the point at the origin stays there. 0 times 3 is still 3. Or, no, I said that wrong. 0 times 3 is 0, still 0. The point 1, 1, I take the x value, I multiply it by 3, and it moves to 3, 1. The point 4, 2, I take the x value, I move it, multiply it by 3. That's going to move all the way out here to 12, x equal 12. And there is a picture of my square root function with that horizontal stretch. All right, 2 more transformations. What if we put negatives either outside of our function or inside of our function? These are going to give us reflections. If the negative is outside of the function, output transformation, that is going to change the sign of the y values. If we change the sign of the y values, that's going to flip the graph or reflect the graph over the x-axis. If the negative is inside the function or inside the parentheses, input transformation, I'm going to change the sign of my x values. If we change the sign of the x values, that's going to take our graph and flip it or reflect it over the y-axis. So for example, if we consider the function f of x equal negative square root of x, my parent function is that square root function, goes to the origin, 1, 1, and 4, 2. The negative is outside of the square root, it's outside of the function. So I'm going to take each of these points and change the sign of the y value. So the point that was at 1, 1 flips and becomes 1, negative 1. The point that was at 4, 2, I change the sign of the y value, it's at 4, negative 2. And what that has done is it has reflected the graph over the x-axis. We've taken all those y values and we've changed their sign. If I put the negative inside the square root, input transformation, now it's the x values that we're changing. Same parent function, but now I'm going to take my x values and change their sign. So the point 1, 1 becomes negative 1, 1. The point 4, 2 becomes negative 4, 2. This is a reflection over or about the y-axis. All right, so to summarize, if we want to graph using graphing transformations, we identify our parent function first, and that's our starting point. Output transformations, things happening outside of that function, are always going to impact the y values. We're going to do exactly what it says. If it says add, we'll add. Multiply, we'll multiply. With output transformations, if you have more than one transformation that you're working on, you are going to follow order of operations, PEMDAS. That means you have to multiply before you can do any addition or subtraction. You're going to be doing your shifts last. If you have things happening inside the function or inside the parentheses, those are input transformations. They're going to impact your x values. You're always going to do the opposite of what it says. Everything is opposite. So if it says add, you'll subtract. If it says multiply, you'll divide, etc. The order is also opposite. You do PEMDAS backwards. Everything is backwards with our input transformations. So if there are multiple input transformations, we're going to actually have to do the shifts first and then deal with any stretching or reflecting. So let's do a couple examples to see how this works. This time we're not actually given an equation, we're just given a graph. So in blue is the graph of y equals f of x. I'm going to see if I can sketch y equals negative f of x plus 1 minus 2. So I'm going to start by just duplicating my parent function onto my graph paper. So I have a starting point. So I basically just tried to trace the parent function, which goes through, let's see, it looks like 0, -1, and then it goes up to 2, 1, and then down to, that looks like 4, -1, and then we've got this horizontal line segment at -1. So I've got 3 different transformations occurring here. I have a negative sign, I have the +1, and the -2. I have both input and output transformations. You can choose to do all of your input transformations first or all of your output transformations. That doesn't matter. I'll do my output transformations first. I have 2 output transformations, the negative sign and the -2. With multiple output transformations, we have to save the shift for the end. So I'm going to deal with the minus first. The minus output impacts y's. We're going to change the sign of all of our y values or reflect our graph over the x-axis. So I took each of the points on this blue graph, the point at 0, -1, I made that 0, 1. The point at 2, 1, I made that 2, -1. So I took each of my points and I changed the sign of the y value. And that basically flips the graph upside down or over that x-axis. All right, now I'm going to do the -2. Output transformation, I do what it says. It says -2. So I'm going to -2 from all my y values, or take this graph and shift it down 2 units. So each of the points, I subtracted 2 from the y values, or brought the entire shape down 2 units. Finally, I've got one more thing to do. This +1 that's inside the parentheses is my input transformation. We're going to do the opposite. It says +1. I'm actually going to -1 from all my x's, and that is going to take my graph and shift it to the left 1 unit. And there's my final answer with those 3 different transformations. Let's do another one that's similar. So let's start with the same parent function. So I'm just going to start over. Same parent function goes through this point 0, -1, 2, 1, 4, -1, and then we've got that horizontal line at -1. Let's see if we can sketch the graph of y equals 2 times f of -x plus 2. Once again, I see both input and output transformations. I'll do my output transformations first. That 2 that's outside of the f of x is being multiplied. Output transformation, it's going to impact our y values. So I'm going to take all of my y values and multiply them by 2. So the point that was at 0, -1 is now at 0, -2. The points that had y values of 0 will stay where they are. The point that was at 2, 1 is now at 2, 2. And my horizontal line, which used to be at -1, has doubled. Now it's at -2. So in green is my graph with that vertical stretch. I've taken the object and stretched it vertically. Now I have 2 different input transformations, the negative sign and the +2. When we have multiple input transformations, we have to do the shifts first. So I'm going to deal with the +2 first. With input transformations, we always do the opposite. It says +2. So I'm going to -2 from all my x values. That's going to take the graph and shift it to the left 2 units. After I do the shift, I'm going to deal with the negative, which is going to change the sign of those x's. All right, so let's do our shift first. So I'm going to take each of my x values and subtract 2. That's going to take this shape in green and move it to the left 2 units. Then I'm going to take that resulting graph and change the sign of all of my x values. That's going to take the graph and flip it or reflect it over the y-axis. So the point that was at 2, negative 2 actually flips and is now at negative 2, negative 2. This horizontal line flips over the y-axis as well and is now on the left side instead of the right side. And there's the graph of this transformed function. Finally, let's take a look at one more example. We should be able to work backwards as well. If we're given a graph, we can come up with the equation. The first step is just to identify the shape. Which of our parent functions does this look like? I see that V shape, so this looks like an absolute value function. Then I'm going to try to identify whether I see any shifts occurring, and it looks like the graph has been shifted to the right 2 units. To shift my function to the right 2 units, I'm going to have to put a -2 inside those absolute values. Then I'm going to see if I have any type of stretch or compression, and the graph does look a little bit steeper. In fact, I can see that the normal absolute value function has a slope of 1, but this one, if I go over 1, I have to go up 2 to get back on the graph. These lines that compose my absolute value function appear to have a slope of 2. That means there was a vertical stretch by a factor of 2. So I'm just going to put a 2 in front of my absolute value function. And this is an equation that matches the graph that we see on the screen. All right, that was my last example. As always, please reach out if anything is unclear.